Okay, so again, the top one is where we're just going to sketch f of x. This second line is the sign chart for the first derivative. So that's going to tell us if the original is increasing or decreasing or not. And then this last one is the second derivative, but it's the sign chart for the second derivative, which we know tells us the concavity of the original. All right, so we're always going to start with the sign chart of the first derivative first. So that's one we always do first, and then we can figure out concavity and go from there. So what I'm doing is relating everything back to the critical values. So we have 1 and 3. So just like I showed you before, if you test 0, then in the first derivative we have a positive, and then let's test 2, negative, test 4, positive. And it doesn't have to be those numbers, but it just has to lie in that interval. So what does this tell us? This tells us for the original f of x, it's increasing, decreasing, and then increasing. So now if we were to sketch it, still with those critical values, we know that it increases, and then since it's a critical value, that's a maximum. Since it's decreasing at this critical value, we have a minimum. That's a very rough sketch clearly, but you get the idea. So then we can do concavity. You could have done that first as well, and just confirm the concavity, or use it when you're graphing in that first one, that sketch of f of x. So the thing here, though, is that concavity changes at the inflection point. So this is where we're going to use a different value. We're going to use 2, because that is the x value of our inflection point. So if we test a point in the second derivative, we have negative. If we test a point in the second derivative above 2, like 3, we get a positive. So this tells us it's going to first concave down, which it does, and then it's going to concave up second, changing at 2, which it does. So now, with all that information, we can draw a very exact sketch. So I'm going to label 1, 2, 3. And then my y values, I'm going to do 1, 2, 3. So we know that one of the roots we have is 1 and 2 point, what is that, 3? So it's a little bit above it. And then we have 3, 1, which is about right here. And then we're going to take it one step further, and we're actually going to find our y-intercept. So since this is the original, I'm just going to look up there. Y-intercept is where we plug 0 in for all the x's, and it's very easy to see it's that constant, which is 1. So according to the sketch that I created to the left, while I was using sign charts for the first and second derivative, I know that we are increasing going through these points. We are decreasing. Oh, that's bad. I don't like that. And then our minimum, there you go, is at 3, and we're going back up. And again, we don't really sketch the inflection point, but if you wanted to go back and say, okay, well, we know it's 2, and then a little above 1, is it there? You can always plot it and then sketch. That's totally fine, too. It's just not what we consider a critical value, but neither is the y-intercept, so that's good. Okay. And then at the bottom it asks, do we have relative or absolute min or max? And these are both relative for the maximum and the minimum. And that's our first example. Okay, so this second example is nicely in factored form for us, but we still need to take the first derivative and then solve for our x value. So, let's see, we're going to need to do the chain rule for this one. So I'm going to bring that 3 down, keep the inside, and then it becomes squared times the derivative of the inside, which is 3. So my first derivative equals 9 times 3x minus 1 squared. So then set it equal to 0. It's very easy to solve for this one because we divide by 9. 9 goes away. We take the square root of 0. That also goes away. So you're actually just looking for the root of the factor here. So our x value is going to be 1/3. Okay, so again, we would divide by 9. It would stay 0 on the left. We would take the square root. It would stay 0 on the left. Then we would add 1, divide by 3, and that's where we get our 1/3. So we have just one critical value here because we start with a cubic, so we know our first derivative is going to be a quadratic. Well, quadratics have 2 roots, but we only found 1 because this is actually has multiplicity, so it's going to hit the x-axis and come right back up, only giving us 1 root. And then when I solve and I go back to the original and I plug in 1/3, I still get 0. All right, and that's going to be important here in 1 second. So my critical value is 1/3. My critical point is 1/3 comma 0. All right, so if we're looking for the inflection point, I'm now going to take the second derivative of x, which turns into, let's see, we're going to bring down a 2 times 9 and get 18. Again, we're doing the chain rule, so we're left with 3x minus 1, and one more time times 3. So my second derivative is equal to 54, 3x minus 1. And sorry in advance for the background music and noise of Abel. All right, so we set that equal to 0, and we solve. And it's going to look very similar. If we divide by 54, on both sides it's going to stay 0, and then we're going to add 1, divide by 3. So now we have the same value for our inflection point. And when I find the y, again, we plug it back into the original. I'm going to get out 0. So if you remember from the first page, if our first and second derivative of a value both gives us 0, then we're going to have a shelf. Okay? So that will actually appear down here. And if you notice that right away, you might even just want to say that we have a shelf at x equals 1/3 for our f of x. All right, so I'm going to draw my 3 tests at the bottom here and then start filling them out so I can have a exact sketch here. Okay, so we're going to start with the first derivative and plot our, or put our critical value on the number line, which is 1/3. We only have 1, so that's all we need. So then when I test the point to the left and right, they are both positive, which means the original is going to increase on this whole domain. Well, if we talked about concavity, now our inflection point, because it's a shelf, our inflection point also has the same value, because usually that's the one that's different. So in the second derivative, if I plug in something to the left of 1/3, I get a negative, which means concave down, and then a number to the right of 1/3, I get a positive, which means concave up. So at 1/3 on our original, we have to concave down, but yet we're going to increase. So that's going to look like this. And then now we still need to increase, but now we're concaving up. And then you could see we just created a shelf there. So there's not much more to this. We have 1/3. This is our root. We know we're going to go up and then back down. So the only thing that we can I'm actually going to scoot that over a little bit. The only thing we can sketch some more is the y-intercept. And when I plug into the original, I have 3 times 0. I plug in 0 for x. I get -1 to the 3rd, which equals -1. So that is my y-intercept. So these are the 2 points that I know. I'm going to concave up. There's going to be that wasn't good. concave up, there's going to be a shelf, and then, oh, it's going to look something like that. And again, it's a little bit curvy. Yeah, say hi, buddy. Say hi. Sorry, guys. Okay, and then the question is it a relative or an absolute min or max? Well, there's none. So fill this out. There's none. There's neither because there's a shelf. You're not going to have a min or a maximum. Okay, our third example. So here we have a quadratic. So we're going to keep doing the same thing, and our first step is to take the first derivative and set it equal to 0. So the first derivative using the power rule is going to be 1/2 minus 1. Set it equal to 0. And we get x equals 2. That is our critical value. We take 2, we plug it into the original, and we get 1. So we have a critical point at 2, 1. So since the original is a quadratic, we're only going to have one critical point because it's only going to have one min or max because we know what a parabola looks like. Buddy, you got to let me do this. All right, so the inflection point. So we need to figure out what the second derivative is. And when I do the power rule to the first derivative, I get just 1/2. Well, if I set this equal to 0, I get 0 equals 1/2. Well, that's not true. And I can't substitute this in for anything. X or 0 does not equal 1/2. So there's no inflection point. All right, so if there's no inflection point, that implies that we're going to have either all concave up or all concave down. All right, so let's go to our sign charts down here. Okay, so we're going to start with the first derivative at 2. If I plug 1 in, or 0, that's easy, I'm going to get a negative, which implies that the original is going to decrease. And then if I plug 3 in, I'm going to get a positive, so we're going to increase on the original. Okay, so it's really important, guys, that down here when you write increase or decrease, we're talking about what f of x is doing. Okay, so then, let's see. If we know that we're just going to increase and then all of a sudden at a point, decrease, and then at a point we're going to increase, that implies that this whole function, since there is no inflection point, I can't graph it, is positive. Okay, and how do we know it's positive? Well, the second derivative is positive 1/2. So therefore, we're going to concave up the whole time. So now we know our original is a parabola, which confirms our concave up. So at 2, it's going to do something like this. Okay? Now, keep in mind, when I sketch these graphs, as it looks like it goes below the number. This is just a number line. This right here is not the x-axis. So don't take that as I know it goes negative, because when you graph this and when you look at our critical point, it actually is not going to go it's not going to become negative at all. So, hold on, buddy. Don't take my paper. All right, so almost done. So we know that at 2, 1, we have our critical point, which we know is a minimum because it's concaving up the whole time. And then our y-intercept, if we look up at the original of f of x, is 2. So as long as I go through that point, and that's my minimum, then we have our graph. And again, this one is actually going to be an absolute minimum. Okay, so what I want you to do now is complete example 4 on your own. There's no guided notes, but we just did 3 examples that all followed the same steps. So follow those same steps, complete number 4. That is what I'm going to check the next time I see you in class. And I hope you have a good afternoon.